So, welcome to the lecture 8 of Photographic Technology. And so my name is Rom Clement. I did the third lecture on ray tracing. And today I'm going to talk about diffraction. And by pursuing the math of diffraction, we'll talk about diffraction gratings and how they're extremely useful for spectroscopy, which is the analysis of the light. So, diffraction. Before talking about diffraction, we need to know a little bit what light is. So, light is an electromagnetic waves made of a magnetic field, H, and an electric field, E. And in everything that we're going to do here, we need to have an understanding of what the intensity of light is. So the intensity of light is the time average of the Poynting vector, but in everything that we're going to do today, we will consider the wave as or the light as a plane wave, and basically the intensity of light will be proportional to E square or to the amplitude of the light square. So that would be a lot more easier to compute the total intensity. So just a couple of assumptions to simplify all the math. We will consider that we are in a linear media, homogeneous and isotropic. As I said before, that we're far enough from the light source so that the light is or can be considered as a plane wave. And with all this different assumption and assuming that we don't have charges in the media or that we don't have current in the media, the Maxwell's equations are a lot more simplified. So first experiment that probably a lot of you has seen at high school is the Young experiment. So using a source S and two holes, S1 and S2, in a sort of sheet of paper, if I'm looking on the other side of this sheet of paper with these two openings, on a screen or on the wall, a couple of meters away from this sheet, if these holes are actually slots, I have this variation of contrast on my wall, so stripes of black stripes and white stripes. So the if we do the math, so the intensity, which is proportional again to E square, is not only the superposition of I1 and I2, which would be the intensity from the electric field E1 coming from the source S1, plus the intensity from the source S2 with the electric field E2, but there's a coupling J1, 2, in which there is modulation of the two intensity, and so delta is what is called or is coming from the difference of optical path, which means that the distance S1 to P, where P is the point where I'm looking at in my screen, is different. So this distance minus S1 is different than this distance minus S2. So everything that we're going to do, and mainly for diffraction, is based on this aspect, which is that because I will have a slightly different optical path, I will create constrictive or destructive interferences. And I won't go into too many details, but in the case of the Young experiment, it is very, very important that in order to have interferences, that we have the same wavelength, that we have the same sources, because the source S1 and S2 seems to be different, let's say, on the right side of the drawing, but they're actually coming from the same source S. And it is related to the notion of coherence length of the source. But again, I won't talk in too many details about that. So what's diffraction? Diffraction occurs when the wavelength of the wave, So it can be light, of course, infrared, ultraviolet, but any phenomena which can be described as a wave. So when this wavelength has about the same size as an object, then diffraction can occur. So for very simple case is just a very tiny needle hole in a sheet of paper where we can have diffraction for the visible light. Or even an open door in a wall would generate diffraction for a wave which would be around 100 megahertz. And so we'll see in much more details the expression of an accurate expression of the angle of diffraction. But as a first feeling, what's happening is that the angle is proportional to the wavelength over A, where A would be the aperture or the diameter of the hole. So I don't want to scare you with the math, but just to give you a feeling of how diffraction is computed. So I have an opening, I have an aperture in a sheet of paper, for instance. I have a point source, P0, which is, again, assumed pretty far from this aperture so that the incoming beam of light is parallel and that I have a plane waves. And I'm looking at this aperture from the point P, which is therefore behind this aperture. And so the amplitude of the wavefront view from this point P, it can be simply expressed as the integral over the aperture of the incoming light. So in our case, we will consider that this pupil function is equal to 1 when we're inside the opening and equal to 0. So the first example, which is done very often because it can be computed by hand, is just a rectangular aperture, with 2A and height 2B. And so if we're computing the amplitude, so U, over this aperture, so we're doing the integral over the surface, what's happening is that the intensity, which is proportional to the amplitude square, is the product of the sinus C function, so sinus x over x. So looking in 3D to this formula or expression of the intensity, so we have a pretty important peak in the middle, but then, as we can see also on the left pictures, on the picture on the left, we also have secondary waves in these two directions. So that's diffraction, and that's pretty far from what we could have, let's say, presume, where we would have believed that, well, it's a rectangular aperture, so I should see a pretty well and very sharp rectangle in my on my screen or on my wall or in my focal plane. But unfortunately, because this aperture is pretty small or is about the same as the wavelengths of the light, I have this pretty big pattern. If we're looking at a circular aperture, which is the most common case, because most of the optics usually are circular, the expression is a little bit different. It is the J1, which is the Bessel function, but it has the same, let's say, characteristics. So a very clear spot in the middle, and then we see a first ring of light, and then a third one, and so on and so forth. So yeah, this is just to see the difference between the two. So it's normalized, of course, to 1 for the maximum, but the secondary peak in the case of a rectangular aperture is about less than 5% of the total, and the second one is about, well, it's less than 2%. It's even less for the circular opening or circular aperture, but as we will see, the problem is how to define the spot. This is just another illustration of, so they're slightly different, but it has the same characteristic. One big peak in the middle and secondary peaks on the sides. So this is the sort of, this is a problem because we were, for instance, let's assume we were using a telescope and that we were looking at a star, so which can be nearly considered as a perfect point source. Instead of having a perfect tiny spot in my focal plane, I have this shape or this profile of intensity. So how can I define my, or let's say, when do I say that I can consider that the remaining energy or the remaining intensity is negligible? So the first peak contains already about 84% of the total intensity, the second one about 91, and the third one about 94. But this is probably not sufficient if we want to, if we consider now the case where we would have two stars. So I have here, I'm looking, for instance, at two stars which has the same intensity. And here, well, they're pretty well, separated in my focal plane. But now, let's assume that they're getting closer. So same intensity for these two. What's start to happen is that, so I have a first peak in the blue curve for my first star, and then I have a second peak in which is my second star. But in reality, the intensity is the sum of the two. So now I'll start to have, let's say, a minimum locally between my two spots. And things are getting, I mean, my total profile is growing, or my minimum local is increasing up to the point where, well, now the total is only one peak. So there's no way for me to tell that there was initially two stars and not only one star. So if I just go back here, can I say that I have two peak or two stars? Well, it's not that trivial, because we need to take into account this is the continuous domain. But in reality, I will have a certain spatial resolution of my film or a certain size of pixels. So if I keep going, of course, the peak is growing in intensity up to the point where my two initial profile of spots are completely merged, and the total intensity is twice the initial of the two. So there was a lot of people has worked on this problem in the past in order to define a criterion which would allow us to tell or to say that, yes, we can say that there is two spots, or no, beyond this point we cannot. So the first person who's talked about this, as far as I've found, was EngEDU, who so gave this criteria, which is that, so the angular aperture theta of the peak, or let's say under the angular aperture theta AB, which is equal to 1.2196, lambda over d, d being the aperture of the telescope or the aperture of the optics. So if I go under this angular or this angle, I will not be able to tell that there is two peaks. Rayleigh had a different approach, which was a lot more based on the Bessel's function and the area disk. The area disk is the first zero of the Bessel function. So let's say it's the middle of the first black circle that you've seen previously. And the result was nearly the same, if not identical. So this is the Rayleigh criterion. So as you can see, what's happening is that the middle of the first spot is precisely located in the zero of the second spot. And so the total intensity or total profile of intensity in the red curve has this minimum local right in the middle. But this is not the only criteria. Sparrow came with another one, which is based on the minimum local of the two peak. And so when the sum of the two peak is slightly flat, or perfectly flat, just as for this optimum, then what's happening is the angular resolution is 0.94. So it's less drastic than the Rayleigh criteria. And there is a fourth one, which is the Houston criterion, which is, in this case, is based on the full width at half maximum. So again, it's a little bit different than previously. But generally speaking, you have the idea that using this criterion, I have an angle under which, well, and if I go under this angle, there is no way for me to tell you or to get more information. So, as I said before, this is the continuous, previously that was the continuous domain. So we could tell that indeed, we could see that there were indeed two small peaks in this total bigger peak. But we need now to add a sensor and therefore spatial resolution. So let's start first with the first sensor. So this is one pixel, and the second one, and the third one. And so what's going to happen here is that my pixel in the middle is basically going to collect all the intensity of light contained in the two peaks, whereas the otherwise will barely get this, let's say, secondary and tertiary peaks. And if I count my electrons in my CCD or in this pixel, I will have a lot of electrons in the pixel in the middle, but nearly nothing in the remaining two. So when I will just display the picture on my screen, I will just see barely zero and then a peak in the middle. So there's no way I can extract the two peak or say that there's two peaks. So if I now take smaller pixels, so one in the middle will collect a certain proportion of the two, and unfortunately, finally, I will have a larger peak, but again, it's going to be one peak. So again, I need to decrease, again, the size of the pixels up to this point where I will have basically 3 pixels at the bottom of my 2 peaks, and the one in the middle would be slightly less than these two, so that I will be able to tell, well, there is a first peak, and then it goes down, and then I get a third peak. So I basically need to have 3 pixels contained within the two zeros of, or between the two zero of my total function, which is so the sum of the two spots. And this is what is just called the Nyquist criteria. So the optimum is when I have 2 pixels inside my area disk, or so 2 pixels for inside my peak, my main and principal peak. And of course, if we don't want to be under or over sampled, because if I'm undersampled, it just means that I have a very, very good optical system, and I'm not using the appropriate sensor or CCD, or I could get a lot more information and a lot more resolution if I was using a CCD with smaller pixels. On the other hand, I don't want to be oversampled, because it means that I have too many pixels and inside my area disk, and maybe I should get another sensor with bigger pixels, which would just a second, which would have, so maybe bigger pixel and might be cheaper, or I would might be also have a shorter exposure time. Yes?
Well, in the undersampling case, you demolish the signal. In the oversampling case, you may have too many samples, but
That's true.
you haven't lost any signal.
Yes, but yeah, yeah, that's very true. So yeah, just a very, very quick example, just to explain that it is not only due to, diffraction is not only due because I have an aperture, and diffraction also occur when with straight edges. So for instance, in this case, if I, following in the W direction, the intensity profile, what's happening is so very, very far up behind my straight edge, so it's completely black, so I don't have any light. But if I go down my screen, what's going to happen is my intensity of light will increase, or I will have some light behind my straight edge. So yeah, so right here, I will get, for instance, well, right here, as seen on the curve here, I will have 25% of the light, and then I will have a certain oscillation of the intensity, and then it goes to converge to 1. So the math are a little bit tricky, but it's interesting. So now let's apply or look at diffraction gratings and how they can be very, very useful for spectroscopy. So I guess I'll try not to spend too much time on this slide. So spectroscopy is the analysis of light. And as I guess everybody has already done this before, if I'm using a perfectly white light, just a simple bulb, and if I'm using a prism, I have a rainbow going from the red, if not ultra-red, down to the violet, if not also ultraviolet. So this is called a continuous spectrum. But if we're looking at a star, or if we're looking at a sodium lamp or mercury lamp, the spectrum of such a device is not continuous. It is it has very, very well defined lines, which are very well defined colors, and what we're seeing is actually the total and the sum of these different colors. Let's say that the emission spectrum bar, so the opposite of an emission spectrum would be an absorption spectrum, where I would have white light, but between my instrument, my spectroscope, and this source of light, I can have a gas, and this gas will absorb certain wavelength, precise wavelength. So in a continuous spectrum, I'll have absorption lines, or black black lines. By analyzing this black line, I will be able to extract information of my gas, so the constitution of my gas or the molecules of my gas. So here, on these drawings, prisms can be used for scattering the light and obtaining a spectrum. But we can also use different devices called gratings, which are based on diffraction, to do the same thing and to obtain the same thing. Yeah, I won't spend a lot of time on this slide. So it's the concept of emission and absorption. So atoms are capturing or emitting energy, and if the level of energy is sufficient enough, it can be light. And by changing the level of energy of the electrons, we're releasing or atoms are releasing very accurate in terms of wavelength or level of energy, which is equivalent photons. So in spectroscopy, we're very interested in the analysis of the lines because a line is a very well, if the line is thin enough, we can determine very well the wavelength, and from the wavelength we can extract the energy of the photons, and from this energy we can extract the type of atoms or the type of molecules from which this photons has been emitted or absorbed. But we can do also a lot more than just studying the position of these lines, of the wavelengths of this line, by studying their distortions. So we can extract, depending on the level of resolution of the spectroscope, but the thermal environment of the source, the pressure, the magnetic field, the electric field, as well as also the velocity of the source. But as you can see, for certain type of such as the Zeeman effect for the magnetic field, we really need to go to a very high resolution of the spectroscope. And in order to have access to this type of information, we really need to scatter the light a lot. In other words, we really need to have a very long spectrogram in order to see and to look into very tiny details the lines.
Those measurements then are required?
Yes. So gratings. So I'll just show you pictures of what they look like in reality. But the principles of gratings is kind of simple. It's a repetition of a pattern, and this pattern, or because of this repetition, we will introduce very tiny difference of optical path, which at the very end will induce interferences, and we'll see how to extract information. So in the first case at the top left, it's a sine wave spectroscope. They're used in holography. We can also find a kind of so shape of the spectroscope for certain gratings. I'm sorry, or even this kind of step gratings at the bottom. And yeah, very common example of gratings are CDs, or CDs and DVDs are not gratings, but because we have this repetition of these lines on a CD or a DVD, or also on credit cards, holograms, we can see the iridescence on these devices. So this is, for instance, what gratings look like. So on the left, you have a reflective grating. So I will explain on the next slide how they made, but they're usually about this size. You can also find smaller one, a couple of centimeters square. And they're also, most of the time, glued on a very, quite thick piece of substrate or glass just to be very flat and stiff. You can also have a second type of gratings, which are transmission gratings, where most of the time they look like just small slides. So the way it's working is, so the light, or in the case of transmission gratings, is coming from one side and is to go through the gratings, and the light is diffracted according to certain orders. I will explain later what an order is. And in the case of reflective gratings, it's the same thing, but with reflection. So reflective gratings are made of, so the grating itself, so the shape of the top itself is usually made with a mold, and so it's an epoxy layer, and then the epoxy is glued on a thick substrate or thick piece of glass, and then a coating is added on the top. And what is quite useful too is that we can tune using what is called the blade's angle. We can tune the angle of the waves so that we will focus more the light or more intensity in a specific order. But again, I will talk about what's an order just later. Yeah, so for the case of refractive gratings, the cost is about a couple of $100s. It's a lot cheaper for transmission gratings, but it's harder to get a higher number of lines or grooves per millimeter, and they're also lower. They have also lower efficiency. So again, I don't want to scare you. It's just I'm just trying to give you a sense of what's happening. So let's do the math for transmission gratings. If we're assuming so transmission grating made of n slits or n slots, each slot has an aperture S, and the distance between the slots is d. So if I'm just considering two beams, because the second beam will go through a different slot, I introduce a difference of optical path, delta, which is proportional to the distance between these two slots, but also proportional to the difference of the incident beam and my diffracted beam. So if we sum everything, I mean all this variation of amplitude and difference of phase for all these amplitudes, for all these beams, the function, I mean this function is appearing. So the total intensity is proportional to this function times I0, where I0 it's just the intensity of one's slot. So I've just copied the previous formula. So I have one function which is the product, which is due to my n slots, which has this shape, times the initial profile so it's a slot, so it's a rectangular aperture with a very long, let's say, width versus height. And the total of these two leads to this function where I have what is called here the order 0, so the maximum of intensity in the middle, but then at a very well-defined angle, which is lambda over d, and unfortunately it might be hard to read it, I have a second peak, and at another angle, 2 lambda over d, I have a third peak, so called respectively the order number 1 and the order number 2. So what's very important here is that at a very precise angle, lambda over d, I know that I'm looking at a specific wavelength, or at a very well-known wavelength. And and if I'm increasing or doubling this angle, I know that I will also looking at the same wavelength. So this is how things are working for transmission gratings and reflective gratings. So if you want to use gratings, these two formula are the references. It's working all the time. So if I'm just looking at the transmission gratings, what's happening is I have an incident beam of light with a given angle theta 0, and if I'm looking on the other side of my gratings at the order theta 0, I'm just looking at the straight light which has not been diffracted. So I have basically the image of my source. But then, because I have 2,000 grooves per millimeter in this gratings, what's happening is if I'm looking on the side behind my gratings, if I'm looking on the side, I will start to see a first peak of light, assuming that that my point source only have one wavelength which is called the order 1. And if I keep going, I will see my second order, so order 0. But the phenomena is completely symmetrical. So if I'm just going back to my order 0 and moving by another angle, but on the left side, I will see my order -1 and order -2 as well. And the same system same phenomena is occurring for the reflective gratings. So this is the simple case where I'm looking at a source which has one wavelength. But now let's assume that I am looking at a source whose wavelength is within the visible spectrum, and just let's consider that I have two wavelengths. So lambda 1, 400 nanometers, and lambda 2, 800 nanometers. So if I'm looking at my first order, M1, my first wavelength, so blue, which would be very, very blue actually, is I will see it at 12.3 degrees. My second wavelength I will see it at 14.7. Now, if I'm looking at my order number 2, the first wavelength, so the blue one, will occur at 14.7, so very, very close to my red line. And my second wavelength will be at 19.5 degrees. But if I keep going and look at the third order, well, it's getting pretty annoying because my first wavelength is at 17 degrees. So my first wavelength is before my red wavelength that I had in the previous order. So what's happening here is that I have an overlap of my orders. So if we're looking at the graph at the top, so I have my first order and then my second order. But we can see that the third order overlaps the second order as the fourth. And things are getting worse and worse and worse and worse. So you would say, well, what's the point of looking at the second or third order if I know that I will have an overlap? Well, the first thing is if you can have, or if you can extract information in the first order, can be just better to do the same with the second and fourth order because you would have 3 measurements. And at least you would have 3 measurements on the positive side for the positive orders. If you multiply this by the number of measurements you can have in the negative orders, you just have more measurements. But the second thing too that you can see here is that the width of, or the length of the second order is bigger than the first. And the fifth is a lot bigger than the fourth or the third. So in other words, my spectrum in the higher orders is a lot longer. And I can extract a lot more information because I can see a lot more details in this spectrum. The small problem we have on top of that too is that unfortunately the intensity of light goes down while the order number is increasing. So this is just, for instance, an example of what you could see using a transmission gratings and a telescope. So in the focal plane, you would see the order 0, which is just straight light coming from the star, so it's not diffracted, so it's the image of the star. But then, at a given angle or at a given distance, once you're using a lens, an optical system to focus the image, you can see the order 1, and well, you can barely see the order 2, but actually it's better on my screen, and so on and so forth. And in this case, for instance, you can see the big advantage of blazing, because you can see that the intensity of the order 1 is higher than the order -1. So it's by tuning the shape of the grooves, we can put more intensity in one order versus another. Yes, I'm sorry? Was it your questions? Okay. So yeah, this is an example of a spectroscope that I made a couple of years ago. It's for a telescope. So you're putting this in the back of the telescope. I was using a collimator, which is just a zoom to make sure that the beam of light, which is going to reach, maybe I should. So the light is entering here, is going through the collimator, and is diffracted with this reflective gratings, and then the light is converging, using the optics to the CCD sensor, which was, in this case, the modified webcam cooled it down to decrease the noise. So yeah, the very important thing is, first of all, to use a collimator to be sure that the incident beam is perfectly parallel to the reflective gratings. And the second thing is that you really need to have a very, very stable rotating system, just to be sure that your reflective gratings, when you will turn it to look at the different orders, so first order first and then second order, will remain perfectly parallel. So yeah, the procedure to extract, once you get, so this, for instance, we're in the red in this case, so you see, because we're using because it's a star, so we have this line inside or matrix, and we need to correct it and align it, binding it, and then import it into a software in order to normalize the spectrum in intensity, but also because the angular dispersion is not linear, we need to adjust a little bit the spectrum and to extract the response of the instrument. And this is, for instance, what you can get by stitching different spectrums of the same star, obviously. But you can see that using, I think it's 1,200 grooves per millimeters in the system that you've seen, I've been able to, I think the resolution was something at 3 angstroms. So you're able to tell that well, I don't have a zoom, but I was barely able to tell that there was 2 peaks of the sodium. I mean, these 2 peaks in the sodium are very, very, very common. Sodium has 2, so 2 peaks at 90 and 96. So 6 angstrom of differences between these 2 peaks. So it's pretty cool to be able to tell the composition of the outer layers of a star using this simple device, as well as to be able to tell that there is no O2 in this star, which is pretty normal because this is the O2 from the atmosphere. And there's also another one. So the first thing I would like to highlight is that diffraction is just it's just coming from the wave approach of light. So that's the reason why it's also working for sound. A perfect point will be, unfortunately, always diffracted because we have an aperture, because in all the devices that we're using, well, there is a finite aperture in all the optical components that we're using. So the diffracted pattern is called, Iridescence is a lot more specific to circular apertures, but it's maybe 95%, if not 99% of optical system are circular. But it's the shape of, or the intensity profile is looks always kind of main peak in the middle and then a small wave at the bottom. And so it's not only true, but it's very, very true for telescope, for instance, that diffraction will usually size the aperture of your system. If you want a given resolution, you will need a certain aperture. And this is coming directly from diffraction. And diffraction can also size to a certain extent the spatial resolution of your system. I mean, you don't want to be under or oversampled, so you may use a given sensor just to fit the iridescence of your optical system. So that's about all the bad news about diffraction, because diffraction is annoying. Diffraction, yeah, I mean, it forced us to have 8 meters telescopes to be able to tell that, well, in this nebula, there was not 2 stars, but there were 10 of them, 100 of them. So it's big and small. It makes things more expensive. But on the other hand, diffraction is pretty cool, as we've seen for gratings, and it's very, very useful. And I would say that the beauty of this is that, so it's tiny grooves, yes indeed, we're 1,000 lines per millimeters, but what's very amazing is by using this, we're able to extract an information which is in the order of an angstrom. So it's a factor of 1,000, which is gain in terms of size, in terms of scales. So that's, yeah, diffraction is bad, but diffraction is sometimes pretty good. Okay.
In time series analysis, we run into a similar thing we call a windowing in that context. And we reduce the side lobes, which I guess are analogous to your diffraction rating by center weighting the signal, by applying a window to the signal that weights the center more than the edges. And that reduces these side lobes. Do you do a similar thing in optics? Is there an analogy there?
I honestly don't know. I'm sorry?
Apodizing a lens could be considering windowing the spectrum sampled.
What do you mean by apodizing? Apochromatic? Yeah.
Putting a sphere out of the focal plane to diminish light in the center portion of the lens.
To diminish it in the center? Yeah, in the time series case, it would be the opposite.
What you want to do is roll off the high frequency.
It's still fundamentally different, though. There's no transform domain here.
Yeah.
This is all in the spatial domain.
But a lens is a Fourier transform, right?
Yes.
And you could apply effectively a sharpening filter or something that was attempting to account for that. But I don't think that sync function is convertible.
Well, it's not invertible, but you can reduce the side lobe by essentially.
But you have to integrate over the entire area.
You have to do a transform, right?
Yeah, I mean, somebody would have done it probably.
Yeah. One quick question. So for most lenses, the number of blades forming the aperture is, 6 or 8 or some variable number, roughly hexagonal. Is the multi-mode function bounded between the perfect spherical and the square case for traditional lenses?
I'm not sure I understand
So
what.
you showed the diffraction pattern and
Yes.
the side lobe behavior for a round aperture and for a square aperture.
Yes.
For hex or octagonal apertures,
Oh.
would it be roughly bounded between the spherical and the circular?
Yes. With a lot more direction, with six directions. Yes.
Okay.
Yes. Yeah, I think the math can be done.
But I definitely get the flare is hex-shaped.
But yeah, the annoying thing is that regardless of the secondary peaks, which does not contain that much of energy, the main issue is that, well, this first peak has a certain width, and this is what is limiting my the resolution. Assuming that I will find the appropriate sensor with this very, very small pixels, which is something I might not be able to find, or if I can find this very, very small, sensor with very, very small pixels, I won't get enough photons.
And so for astrophotography, I can see this a little bit easier. For traditional photography, or what's the aperture where we really need to start worrying about diffraction effects compared to traditional lens geometric optic aberration? I thought it was relatively small.
Yeah, I didn't do the math, but I found on the web in very, very obvious example where yes, indeed, as you're saying, in most cases right now, in most SLR cameras, the area disk is a lot more smaller than the pixels. So the pixels are usually a lot bigger so far. But if you start to use 500 millimeters lens, you may run into this type of problems. I would say that if the current optics in digital cameras are that big or have this diameter, it's not because of diffraction. It's just because if you have bigger lenses, you'll get more light, and therefore you'll reduce your exposure time.